Let's jump right in. Welcome to this explainer, where we're going to bridge the gap between theoretical physics and real-world structural design. If you've ever looked up at a massive bridge or a high-rise and wondered exactly how engineers literally guarantee it won't collapse, well, you're in the right place. Today, we're taking the foundational concepts of prestressed concrete and turning them into practical, numerical mastery using the Indian Standard Codal provisions.
Okay, here's our blueprint for today. We're going to start with what I call the engineering constitution, then move into the limit state philosophy and break down a step-by-step design procedure. After that, we'll actually put it all into practice, check the ultimate flexural strength, and finally, look beyond basic rectangular sections.
So, Part 1. The Engineering Constitution, specifically IS 1343-2012 and its supporting codes.
You absolutely cannot build a safe structure on guesswork. You need a codified set of rules. I love this quote from Professor Deshmukh. It perfectly frames our master document, IS 1343-2012, as the ultimate authority for pre-stressed concrete design in India. This is literally where you transform from a student who just gets the concept into a full-fledged engineer who can actually design a structure. It contains the whole shebang: materials, design methods, and the strict construction practices that keep our infrastructure standing.
Now, while Section 22.1 of IS 1343 is our absolute main focus today for ultimate flexural strength, we're always relying on an entire ecosystem of supplementary codes. We've got IS 456 for basic plain and reinforced concrete principles. We lean heavily on IS 875 to calculate all our loads, dead, live, and wind. And of course, IS 1785 for the exact specifications of our pre-stressing steel. They all work together like a giant interconnected toolkit.
All right, let's move right along to the underlying philosophy that governs our design, the limit state philosophy, where we balance safety and usability. This is crucial because as an engineer, you have a dual mandate. You have to guarantee the beam has the raw strengths to survive a worst-case scenario, that's your ultimate limit state, but you also have to maintain everyday serviceability. Think about it. It's not enough that a bridge merely stays up. If it bounces wildly or shows massive cracks during a normal traffic jam, it has completely failed its serviceability limit state. So we have to satisfy both the absolute safety of the structure and the everyday comfort of its users.
So how do we actually apply this philosophy in practice without getting totally lost in the math? Let's look at the step-by-step design procedure. The code actually hands us this fantastic, systematic, 6-step blueprint to tackle any flexural design. First, you determine the bending moments from your dead and live loads. Next up, you assume a trial cross-section. From there, you calculate the required pre-stressing force and its eccentricity. Then, and this is a big one, you rigorously check your top and bottom fiber stresses at both the transfer stage and in service. After that, you verify the ultimate flexural strength. And finally, wrap it up with checks for shear and deflection.
Okay, this brings us to the golden rule of flexural design. The factored load the beam experiences must never, ever exceed its calculated ultimate capacity. MU is your ultimate design moment, which is mathematically defined as 1.5 times the sum of your dead load and live load moments. MR is your ultimate moment of resistance, basically the maximum muscular pushback your beam can offer. If MU surpasses MR, well, you have a failure. No two ways about it.
Now, what's really fascinating here is how the code simplifies some pretty complex failure mechanics into a neat rectangular stress block. It's defined by the concrete's characteristic compressive strength, FCK, over a specific neutral axis depth, XU. At the ultimate limit state, the total compressive force pushing against that block of concrete is perfectly balanced by the tensile force pulling on the pre-stressing steel. This is a brilliant simplification because it allows us to calculate ultimate capacity without needing to run complex nonlinear computer models for every single beam we design.
All right, enough theory. Let's get our hands dirty and actually put it into practice by designing a rectangular beam.
Here's our setup for a simply supported rectangular beam. We're spanning 12 meters, and we're dealing with a 5 kilonewton per meter dead load. That's on top of the self-weight, by the way, plus a 10 kilonewton per meter live load. We're using high-strength M50 concrete and 7-wire strands with a characteristic tensile strength of 1860 newtons per square millimeter. Now, to manage these service moments, our preliminary math leads us to assume a section depth of 650 millimeters and a width of 300 millimeters.
So, we need to balance the required area of steel to ensure zero tension at the bottom fiber during service. Why? Because we're designing a Type 1 member where absolutely no tension is allowed under everyday loads.
Doing that math, we calculate a necessary pre-stressing force of approximately 1285 kilonewtons. To actually achieve that massive required force, we're going to need 10 strands of steel. But hold on. Before we look at the extreme failure state, we need to quickly verify what happens at transfer. This is when only the beam's own self-weight and that massive pre-stress force are acting on it. Our top stress calculates out to negative 1.42 newtons per square millimeter, which means it's in tension. However, the allowable tension at transfer for M50 concrete is about 2.0, so we're safely below that limit. This design is totally acceptable, and most importantly, it's not going to crack on day one.
Now for the real climax of our mathematical journey, checking the ultimate flexural strength by applying clause 22.1. We start by applying a 1.5 load factor to our combined self-weight, dead load, and live load. Doing that, we find our ultimate design moment is 536.6 kilonewton meters. This is the absolute maximum punishment the beam will ever reasonably take. This is our target number. Our beam's internal resistance simply has to beat this number.
So, how do we find that resistance? Well, first we calculate our effective reinforcement ratio, which comes out to 0.206 based on our steel area, concrete grade, and section dimensions. Then we flip to Table 11 from IS 1343 for bonded tendons. We can just interpolate our calculated ratio to find our neutral axis depth and stress ratios, entirely skipping any complex calculus. We find our stress ratio is 0.96 and our neutral axis to depth ratio is 0.45. Seriously, the code is practically doing the heavy lifting for us here.
Next, we plug those interpolated values straight into the code's moment of resistance formula. We multiply our design stress in the tendon by the area of steel, and then multiply that whole thing by our lever arm. What does that give us? An ultimate capacity of an impressive 738.5 kilonewton meters.
And there it is, the definitive resolution to our engineering problem. Since our ultimate design moment of 536.6 is far less than our calculated resistance of 738.5, the design is unequivocally safe. We've got a really healthy margin here, which means we have successfully satisfied the ultimate limit state requirements.
Before we wrap this up, let's briefly look beyond rectangular sections. We need to talk about flanges and unbonded tendons.
It's vital to recognize that these exact same principles apply to more complex shapes. The code provides specific adaptations for flanged bridge sections, like I-beams and T-beams, and for post-tension slabs. It's pretty straightforward. If the neutral axis stays in the flange, you just treat it like a wide rectangle. But if it drops into the web, you have to account for both the flange and the web in your compression block. And if you happen to be using unbonded tendons, where the strain isn't perfectly compatible with the surrounding concrete, IS 1343 gives you a completely separate table, Table 12, to determine your stress based on the span to depth ratio. The beautiful thing is, the limit state philosophy remains completely consistent no matter the structural form.
I'd highly recommend grabbing a screenshot of this summary table. It distills literally everything we've covered today from clause 22.1 into your essential engineering toolkit. It gives you the ultimate check criteria, the formula for the effective reinforcement ratio, the calculation for the ultimate moment of resistance, and the required design load factoring. Whenever you're applying the code, this is exactly the reference guide you'll want on hand.
Now, you might be asking yourself, hey, we just did all this design work for strength, but what about the cracking we explicitly wanted to avoid? And that is the perfect question to really understand why we did all this math. Think back to our dual mandate from the beginning. The ultimate check, that massive 738.5 kilonewton meter capacity, ensures the beam absolutely will not collapse. But those careful stress checks we did earlier at transfer and service, those are what ensure it won't crack under everyday normal loads. And honestly, that is the true elegance of the limit state method.
Okay, so the ultimate check guarantees it won't collapse, but it's up to you to test the limits. Because our resistance was so much higher than our required moment, we definitely have some room for economy here. So here's a homework challenge for you. Try running the numbers again, but with just 8 strands instead of 10. Does it still satisfy the ultimate condition? See if you can hit that sweet spot balancing flawless safety with economic efficiency. That's what true engineering is all about, right? Thanks for joining this explainer, and keep exploring the science that holds a world together.